Alrighty, folks, I hope you are doing well. We are going to jump in and talk about a rendering technique and do a little bit of recap on final project stuff, just to get everybody acquainted. We are, I can't believe it, already into module 11, and going to be really wrapping up the course relatively fast in the next week. So let me go ahead and bring up the course calendar here. And just to give us a light of where we're at, we're going to have module number 11 here, photon mapping. Module number 12, I'm actually going to give us a day off on Friday so you can work on your projects and move parallelization and talk about that in week 7. And then we'll do sort of a wrap up of the course, and that'll be it. Your assignment 4, which I'll make a note and update on the calendar here, but it'll also be due on the 20th with your project. And I'm going to spend a little bit of time today in lecture to talk about the final project, just to make sure that everybody's on the same page there. So with that said, let's go ahead and jump into today's module and move along here. So what I have here for today is a nice warm-up here, which is a free book. I always love free books, plenty to read here. And this is actually the second book in a series of the Ray Tracing Gems series. Ray Tracing Gems 1 and now 2 are free. Version 2 has been announced free as of SIGGRAPH, so if you go ahead and take a look at it, you can download a digital PDF of the book here. I highly recommend it. Yeah, I'll accept all these cookies and stuff. And you can see some of the topics that we did talk about here from our author, Peter Shirley, as well as folks that we've mentioned, like Morgan and some others as well. And this second book really does give some nice discussion on things that we have talked about, whether it's reflection or refraction. I think we've mentioned Fresnel briefly, motion blur, some of the different corner cases, and just some other topics here. And then it goes on and talks a little bit about some of the other tools and things like real-time ray tracing, which is how we're going to probably wrap up the course in our wrap-up, because that'll be the next or the last item to really look at for us. Anyway, this book's a nice reference, and I would also recommend the second book. Another one of the topics, discussion of axis-aligned bounding boxes, as I mentioned, by Shirley. That might also be another interesting topic, and maybe something interesting to implement in your final project, so you have this as another resource as well. If you search the, I believe if I just change this to a 1, let's see if this will give me the Ray Tracing Gems first index here for this page. There we go. There's the Ray Tracing Gems. This is another, again, book. I believe I might have mentioned it, or it's listed on our webpage, but now there's a second one. And there's some of the intersection stuff that we have talked about, again, because that's a big part of ray tracing is also covered here. So it might be things interesting for you to look at. So anyway, I thought that was a neat thing that's out in the community, and always nice when they take some time to make these resources compiled by the experts in the field, the true state-of-the-art folks in ray tracing, and release these things for free. All right, so with that said, though, where were we? We were talking about textures last week, procedural textures, this idea of parameterization and this ability to wrap a texture around a shape and sample from it, and then draw pixels based off of an image, whether that image is something that an artist has drawn or something that is perhaps procedurally generated. So we've talked about how we could perhaps use some noise functions, for example, things like Perlin noise, which is a specific noise function, to generate this sort of noisy shape here and build texture. And you can sort of procedurally generate lots of different shapes and things that are emulated from nature, for example, using this sort of pattern here. So this is the idea here. So while you're not required to implement textures, that could be another perhaps final project to actually texture your objects. That's something we do in the real-time course because it's quite standard, but in the ray tracer, I think it's going further. So that could be a potential final project to perhaps do some procedural textures and then maybe apply them to the objects. I think that would be pretty cool, or load them from another image. Okay. And then the last topic we talked about was emissive light. So this idea that you could create a shape and then just cast rays from it and then add light to your scene in that way. Okay, so you can sort of have another direct lighting source here that lights up the object. So that certainly creates a nice sort of atmosphere, and it kind of changes things, and you can sort of brighten or your scene up and cast more shadows and more secondary rays from this sort of direct lighting source, and sort of make things interesting. And then Shirley uses a box to represent this particular shape, which is pretty cool. So that's something that you can also do. All right, so some logistics. I need to spend some time on logistics as we are wrapping up on this course. And this course, more than any other course, is just flown by. Perhaps it's just summer 2 seems like it's even shorter than summer 1 is in the speed that things go. So A4 has been released. It's been pushed to your repository for a few days now, but I just want to formally go over it with you folks since we haven't done that yet. But it is on doing the triangle, so I know I made mention of it but during the class, but really I just want you to be able to draw a triangular mesh here, okay, in the OBJ format. As has been mentioned. So you'll be able to do that. Load an object file. So there's a little bit of work to be done with parsing a particular file. And you have some of these files available in the common objects folder that you can take a look at and be able to load in your models. And you can hard code which model to load. I don't really care. It's not super specific, but some folks might want the ability to choose which model at runtime. Maybe you can have a default or read something in from the command line arguments. That's fine. Just tell me how to do so in the run.md file that you provide with all of your assignments. Optionally, I have asked for some things during the in-class activities, like motion blur, for instance. If you want to sort of move your model, that could be kind of cool, or the other things that we've had. But really, I just care about being able to load an object model and essentially render triangles. So there's a really nice thing you can do as sort of a progression for this, in that you could just render a single triangle, for example. Just try to be able to draw a triangle by just plotting points or putting in some data. I think that'd be a really good first step, just to make sure that everything's working. Okay, and again, as I mentioned, you don't need a texture or anything for this. Okay, so there's a little bit of notes on the object model file, and that's really it. So that's the goal for assignment 4 here. Okay, so let me jump back to the logistics. That's bullet point number 1. And then the final project specification is being released. So you'll also see that in your repository under final project here. And the goal is a few things that you're going to do. You're going to create a well, let me talk about what the project is, I guess. So final project for this. I'm going to list a few ideas here, but really you could do anything. Maybe that's too wide, but let me just sort of generally say this. I gave some ideas: texturing models, any of the topics that we didn't specifically cover in assignments 1 through 4 that were in the Shirley books, whether that was book 1, 2, or 3, would be final projects. And I'm not expecting you to, for example, look at this book and implement everything, but you might pick one of these topics, for example, and be able to implement this feature here. Okay, so this is sampling only, one of these lights here that's been implemented and sort of having different sampling. And then you could maybe implement an interesting sampling algorithm using some Monte Carlo algorithm or something. So that would be the idea. Visually, I don't care actually if your output of your ray tracer looks, exactly the same as assignment 4, assuming that you've implemented some different algorithm behind the scenes. Okay, I just want you to be able to explore something that's interesting, one of these sort of going further topics in your project. And part of the project, so once you have an idea, and here's a bunch that you could try. If you're really not sure, I would recommend just sticking with something that's covered in the Shirley book, so you have sort of a reference or a scratch pixel, but here's plenty of options here. You can propose something else to me if you have something totally otherwise in mind. We've had at least one folk do that. So that's also an option. So anyway, once you've sort of settled on your idea, you have a deliverable. You're going to deliver a video. So I have some samples of these from my other graphics course on various graphics related projects, but you'll sort of get the idea of how to do this presentation. So it's just a short 2 to 3 minute video I want you to be able to do this as part of your portfolio, because I think it's important. If you're going to apply for a graphics job, for instance, you want to be able to show something off. So if I click on one of these here, you'll get the idea. Once we get past these ads here, you know, and the basic idea is just to talk about what you did. So this person did a nice job talking about their sort of features. They outlined them. You can actually go into the code, show where you did the implementation. I think that's interesting. You know, at this point, it's the end of the semester, so you're welcome to show any of your code, and then actually show off what you rendered. So this person was actually doing terrain rendering. This was a real-time graphics project, but you get the idea. You know, you can show your image, kind of highlight some things that were interesting, and just talk about it, or maybe show different renderings. You know, if you're loading different scenes or whatever in your project. And again, the range is wide in how you present this. Maybe visually you didn't improve anything, but you improved the rendering performance, right? So you could show benchmarks or however you want to sort of sell this to me. That's sort of the idea for your project. And ultimately, I want it to be something that you're interested in, right? I realize everybody who's in this course is in here because they want to learn something graphics, so I'm happy with that. I just want you to push yourself a little bit at the end here, and work on something that's fun for you, and that could, you know, you could potentially continue after the course, right? I think that's more important, you know, that you do this, enjoy it, have fun, more so than the grade, I think, for this particular type of course. Right, so here are some ideas. You'll have your sort of deliverables. You'll need a little run script. I'll make a note of that. And that's it. Now, in theory, you could do this as a team. I think our class is pretty small, so I'd recommend everyone does it individually, but you could do it as a team if you want to propose that last minute and form a team. Okay, so that's on the final project. As I mentioned, Friday, we're going to have an off day just to sort of catch up. This week, I've technically been away at not one, but two conferences, so things have been a little bit chaotic. And I'm also traveling for a few days. But it'll also give me a little bit of time to compile my notes at SIGGRAPH and a little bit of time for you folks to just have sort of one less thing to do, and you can focus on your project instead. Maybe you spend, you know, Friday choosing your project and getting started with that, or just working on A4. I think at this point in the semester, that's important. Okay. So that's the idea. Okay. So no lecture Friday. We'll kind of give us some time to catch up. And I'll also start having some grades rolling in. For the most part, if anybody was concerned, you should be fine if you've been completing the assignments. Again, this is a class that I'm not as concerned with the grades. I'm just excited that folks are here and hopefully learning cool stuff. And still want to check in with folks if possible. If I take us over to Piazza, I just want to get some engagement. It's okay if we don't have time or the ability to do this live, but there is a little win to meet here, just to see if folks would want to meet at some particular time here. So we have one person so far who's answered. So if other folks answer this, we'll try to do a live session. Maybe we can talk about projects, or just talk. Otherwise, I'll just arrange one-on-one with folks if you want to meet. Because we'll just, you know, be happy to meet you folks here. I don't see this course as the end of our graphics. You know, I want to keep in touch for those who are also going to take the real-time course with me, or for those who might want to continue or think about doing projects further. That's the goal here. Okay, so just a few notes on that. If you have any questions, comments, concerns, please let me know. And otherwise, let's go ahead and dive into the topic today. And proceed from there. Okay, so as I mentioned, projects. So key takeaways from today. This idea of photon mapping. I'm going to talk about another sort of rendering technique that you should be aware of. It's not really touched upon in Surely, or at least in the second book. So. Or I guess it's maybe started to touch upon just a little bit in Surely, but we need to talk about it here. And it's this idea of photon mapping. Okay, here's a image of something that's been done with photon mapping. Okay, so typically when we've talked about light so far, you know, we were able to introduce a light source. its light source was emissive in the sense of how it casts new rays outward, right? When we were reviewing this, we talked about, hey, we just create this thing that's going to cast out some rays here. It's sort of a direct light source sending out rays here, okay? And that's pretty cool that we can have these light sources, because previously we've been just casting out rays from our camera or our eye, and, you know, that's been okay too. But it's actually not realistic. You know, it's okay, it's a good enough model, but what we've been actually doing is something known as backwards ray tracing. Okay, so this is, if this is you, let's take a look at this illustration, the bottom figure here. You are essentially casting rays out of your eyes, right? But as we know, your eyes really don't emit light. Okay, they're not really emissive in the way that a lightning bug or a firefly is, depending on how you refer to that. But right, your eyes don't really emit light. Some creatures do. Ours don't really, as humans. Maybe there's a really tiny amount, but you know, of electricity in our eyes. But you know, so we call this backwards ray tracing because we're sort of from our camera emitting light, but in reality, right, the sun is something that emits light, or a flashlight, or some other light source. So we sort of call this backwards ray tracing in this sense that, again, we're casting rays from our eyes and seeing if they hit surfaces rather than from the light sources. Okay, so the good thing about this technique we've been using, though, is computationally, when we speak relative in ray tracing terms, computationally, this is pretty efficient, right? We know we have sort of an m by n, or however many pixels you have, your width times your height, you're going to cast out a ray, and then you test the intersection for every object in the scene here. So it's like some sort of squared algorithm, maybe a cubed algorithm with every object here, and you know, so it is computationally expensive, but for the basic ray tracing algorithm, it's feasible to actually be able to do this, and in some cases we're able to do it in real time. That's what the new hardware today is trying to support, this type of sort of backwards ray tracing model here. Okay, and we've talked about ways that we can make this more efficient with bounding volumes and so on. But if I asked you, and this is a question for you to, you know, pause the video and take a look at, but how would you simulate this effect here if you had to do it in our current model? Would it work with backwards ray tracing? And I'll give you a few moments to think about that. And you know, the answer is it would be really hard to do this, right? So if we just look at this effect here, you know, before we even think about how would we sort of simulate it, let's just see what's kind of interesting. Well, what's really interesting is this light that's sort of gathering under this glass sphere here, right? There's some light passing from this light source here. It's sort of refracting, and it's bending through this sphere, and a sphere is sort of this, you know, it's when the light passes through, it's like a concave shape here, and it's bending the light, and then it's sort of gathering under it right here, right? Just like the shadow sort of gathers into the sphere, but there's also light bent and sort of accumulating here, right? And you can do this experiment if you have a marble, piece of glass, piece of jewelry, something, and shine a light on top of it and see, you know, it's not just a dark sphere under it, like it would be with this metallic figure. If something is translucent or like a glass material, light would pass through and bend, okay? In this sort of wavy light pattern, you also get the same thing that happens on water, for instance. Remember, water is a very important graphics thing to be able to simulate. People, you know, you can very easily tell if a scene is fake if the water is not done realistically, right? So people spend a lot of time, and this is one of the phenomenon that happens on water, this sort of caustic reflection, okay? Now with our backwards ray tracing, since I'm casting the rays just from my camera, where is this light going to bend around? Well, it's going to bend, you know, from, you know, behind this shape, wherever I'm casting. I need actual sort of lights to be able to do this, right? We need some emissive material, I guess, to simulate this and do this phenomenon. But there's a little bit more to it, because there's actually light on the ceiling here too. You know, where does that come from? And I'll actually let me just add that here. You know, what about the indirect light on the ceiling. That's going to be one of our terms today. That's why I wanted to write it down and make sure it's in here. But what about this? You know, because our light source is just casting rays down. So okay, maybe with backward ray tracing we could kind of do this. But the water is actually going to be reflecting some rays up, I guess, and it's going to be bending. But it also needs to accumulate light here. So there's a lot going on here, is what I'm saying. It's going to be hard to simulate with our sort of backward ray tracing technique here. So we need something more powerful. Okay, so what we need is a technique known as photon mapping, and this uses what's called forward ray tracing. And photon mapping is a sort of family of techniques that uses forward ray tracing, which is the opposite of backwards ray tracing. But this is actually from a light source casting all of our rays. Now, if we have something like the sun here, which we have, you'll notice also that these rays are being cast in every possible direction, okay? Like photons would be in a light. You know, they're not concentrated, they're sent out everywhere. So we want to be able to simulate that. And we'd want to be able to simulate a lot of these particles being sent out, okay? So we're casting rays from a light source, and we're sort of casting them from every direction. And what's different this time is each of our shapes here, whatever they are, you know, this sort of mirror or door, whatever the shape is that's reflecting on, it needs two passes to actually properly model this lighting model here. One pass is actually going to be accumulating the actual light that hits the surface, okay? And then we actually do the second pass, this time from our camera to these surfaces, and then we do our sort of regular backward ray tracing in a sense, and see which of the rays sort of intersect with the individual, you know, the photon map, which holds the lighting information here, okay? And then we illuminate objects based off of that, okay? Sort of simulating all of our light sources, collecting all the light on our surfaces in this special sort of texture called a photon map, and then we do the casting. So there's actually two passes in our ray tracer now at this point to properly do photon mapping. Okay, and by doing this, we can simulate this effect. This is what's known as caustics. You see it in the water here. You know, if you've gone in a swimming pool, it's very cool. It's almost relaxing in a way too. In the ability for light to be sort of bent here and form an envelope and so on. Okay, and it just concentrates in this area. Okay, so this is the effect that we get here with photon mapping. And there's a nice student project, actually a bachelor's thesis, that shows where the light's accumulating in these photon maps, and then where that's laid over when you do the ray tracing. And then you can see how this sort of affects the scene here. Okay, so you've probably got some light source over here shining. Okay. So at first glance, you know, when you do your ray tracers, we are producing some pretty cool images. You know, we've got a lot of image correction going on, gamma correction, motion blur, depth of field to sort of focus our image. We've simulated things like shadows, reflections, refractions, and so we get pretty powerful images here, like shown on the left. But on the right here, you'll notice the difference instantly just when you look underneath the shapes and you see this sort of caustics effect and some of the indirect lighting, even on the walls here, right? This just simulates much better what's going on in the real world. I mean, even look at the ceiling of this image here. You can see how it's a little bit brighter here and just the reflections in the wall. There's a nice comparison here of just the different sort of ray tracing. You can see it's pretty fast, 1.5 seconds to generate this image, right? That's we're getting towards real time, right? Maybe with some optimizations, but you start doing some better shadows, right? You have your anti-aliasing here, the soft shadows, sort of doing some sampling here to see how much light accumulates rather than just making things dark. Then you add the caustics, but instantly you see with the two passes, we're at 12 seconds. So, you know, we can say this is 8 times more costly. And then I'm going to talk about this in a second, global illumination, but the image just keeps getting better and better as you're adding more and more lighting simulated, okay? So that's the difference. That's the main takeaway today. If there's a sort of gold nugget here about the difference between what we have been doing with forward versus backward ray tracing. Okay, so just as a review, again, forward ray tracing, we're coming from the light source across a shape testing the sort of intersection that way, accumulating the light, and then later doing a test against our eye if we're doing this photon mapping technique. And with backwards ray tracing, we're just casting rays from our eye, hitting surfaces, and then reflecting them towards light sources to figure out what the color is in just one pass. Okay, so go ahead and give yourself a break if you want. You can go ahead and take a look at some of these images. I would recommend just taking a look at on the resources page today, photon mapping. You can kind of read a little bit about it, and you can really get some of these beautiful images here. Okay, so go ahead and take a pause there and take a look at those articles. If you go ahead and give yourself a little break if you've needed it, let's go ahead and continue. Just a few more slides here to talk about global illumination. Okay, so this is the idea. If you're looking at those different images and wanted to see, okay, how do we get to this really nice image here? And this is something that Shirley starts talking about a little bit, but what we're doing here in this scene is we're actually simulating indirect light that occurs in the scene. So that is, again, that these light sources that we have aren't just casting rays sort of down. The rays are hitting off of something and then they're bouncing. You can also sort of model the photons, I guess, losing their energy in a sense, after each bounce to give sort of softer lighting over time, perhaps. So there's different tricks you can do there. This really simulates better what's going on when you create this scene, right? The ceiling would not be all black here. In fact, when you look at this image on the right and the left, you'll actually start to see that this image doesn't look that nice anymore. Kind of takes away some of the fun here, right? You would not have an all black ceiling with this light here. That just, unless it's a really, really, really dark paint or something, that you just will not have any color, I guess. Okay. Anyway, so that's the idea there with indirect lighting. And here's just another way to look at the scene. And what I mean by global illumination is, usually when we're casting rays from our eye or even from the light source, if we're only doing one at a time, we're not truly capturing all these indirect rays, right? We would have this sort of still primary ray, but we'd have all these sort of secondary rays that are also cast and reflected. And that's what gives us what we call indirect lighting here, okay? Now, why we don't typically do this, or at least why we didn't start in the course by modeling using this technique of global illumination, which takes into account indirect lighting as well as just the direct lights, is, well, we have a bunch of rays here. So in order to figure out what this actual color is of this pixel, we have to take the integral. What's an integral from your calculus days? Don't worry, you don't need to know any calculus, but you just need to know that integral is a summation, right? It's a summation of many parts, right, to compute the area under that curve, but you just think of it as summing up many things versus here where we just have one ray and we're just saying, hey, that's the pixel color here. Right away, we've got it. But here we actually have to do an integral or a summation of many things. Okay, so physics comes into play a little bit here in calculus, and we need a sort of overall sum here. Okay. Now, this is actually the last slide I'll show. It looks scary, but it's not actually too bad. But it's what's known as a rendering equation. You're obligated to show this in a computer graphics class, but the idea is for the number of lights that you have, say just light 0 here on the left side, you have some light source here, and then you have all the indirect lighting, that's this integral here, computing various properties of the light, what direction it's coming from, the normal, what the color is, the color of the wavelength, and all these sort of different things here of both the actual light and then all the indirect lights. And that's where you're doing this summation here. Okay. So you're doing the direct lighting, the light coming down, this is a white light, and then all the indirect lighting is computed in some integral here. Okay, so that's the main idea. And again, because this is an integral, it's going to take longer. You have to sum more things up as opposed to just the light here, right? Previously, we just had sort of this portion of the equation. Okay. So what folks will do is, and just sort of looking at the scene, is they'll say, okay, well, how many indirect rays should we cast? And again, this is something that's tunable, right? We've learned about sampling when we did the anti-aliasing, and we said we do 100 samples per pixel. Well, you can do the same thing with your sort of global illumination model for the indirect lights, and sort of cast rays out in 500 directions or whatever you choose, and just sort of have a fixed number. That's one way to make this problem sort of tractable, meaning that you can solve it in a reasonable enough time, okay, by just casting rays out in a few different directions as opposed to every single direction and trying to get things physically right. Now, if you're Pixar, if you're DreamWorks, if you're a big movie studio, then you can spend time. You have rendering farms to simulate some of these effects and so on, but that's the overall idea, I suppose, that you could do enough to generate a scene like this in 12 seconds. Okay, so that's the topic I wanted to introduce. Make sure that you're aware of global illumination simulates a direct light as well as indirect light, and that we have a new technique, one of many techniques. I might introduce another one, but now you at least know the difference between forward and backward ray tracing, and the truth to what we've been doing is just things backwards to make things run fast enough. Okay, if we want to simulate nice effects, again, final project candidate could be to do some sort of global illumination model, even if it's sort of hacked together. I think Shirley talks about this a little bit, and he goes into Monte Carlo a little bit. That would be also very nice. Okay, so that's where I'll leave this video. I think this is cool stuff. I think the wiki page on photon mapping is a must read, and I think just as a teaser here, let me go to the photon mapping page. I don't have the images uploaded yet, but the readings is really good here in photon mapping if you just want to see an example. Zach Waters was actually my boss a few years ago, so you can read his article he wrote as a undergraduate. So kind of cool. His is still the #1 hit. So a lesson on writing good arguments, good articles. But here he goes to talk a little bit about how to model the photon, storing the sort of energy in this sort of photon map, and then the second pass, which is the rendering, and doing this approximation as we talked about with the rendering equation, right? You can't simulate everything, right? Too many photons would be needed in the photon map to accurately handle things, etc. But you can sort of do a approximation. So he does a nice job sort of talking about this and sampling. So you can see the little sampling, just a few photons, not one for every pixel here. That you can do. So it goes into the rendering equation here, and then he talks about caustics. You can see these nice images that Zach was generating almost 20 years ago, maybe 15 years ago or so, for him, and the nice things that were generated. He actually does this nice job too of showing sort of a debugged view of where the photon map is, right? So in 2 passes you can actually do this. So that's an idea for your ray tracer. You could do something maybe interesting with a final project on this, like adding some cool debugging features. I think that would be pretty cool. Anyway, this is another good read. Still capturing some of the state-of-the-art stuff that we're still doing today, still practical, still valuable. Anyway, I'll leave it there for today. And if you want to practice looking at some of these things, because I want you to practice as well if you're ahead, I would take a look at, let's go to the book #3 and start looking at the Monte Carlo stuff here, which is going to talk a little bit about sort of light, how it works, and then he gets into the sort of sampling idea here and some of the importance there. Okay. And let's see, global, Shirley doesn't even talk about global illumination. It's too bad. I don't think in any of these books he does not address the issue. So a little bit of an advanced topic, but something that's still within range. The Scratch Pixel site maybe touches on the global illumination stuff a little bit, in path tracing, a few chapters here, and an actual implementation here. So this could be, final project resource, a good final project resource. All right, anyway, I said I was going to go, but I get excited about this stuff, so I'll leave it there. And again, enjoy No Module Friday. Take that time to work on your project, catch up on homework, whatever, and enjoy. And then we will touch base very, very soon, folks. All right, take care.